Okay, I guess I'm muted. Good. Okay. Um, so we're going to talk about Fourier transforms, which I don't think I have to convince anyone in physics that Fourier transforms are useful. And I'm going to talk about Fourier transforms in the context of a problem we've talked about a couple of times in this course, because I think it's actually kind of nice to think about it in this context. So I've been going kind of on and on repeatedly about the period doubling route to chaos. And previously we saw this in discrete time dynamical systems, right? So I have this dynamical system, next state is a function of the previous state. And I just said that this oscillates when R is small. When R increases, it oscillates with a longer period. R increases, it oscillates with an even longer period. And eventually when R hits some critical value, that's when I get chaos. And we saw a bunch of examples of bifurcation diagrams where you see this route where the period doubles, it doubles, it doubles until eventually it's not periodic at all. You get chaos. Okay, so period doubling, I've only been talking about in the context of what I think could fairly be described as a very contrived situation, right? This doesn't seem that much like a real system. But it turns out that this mechanism by which you give rise to chaos is actually extremely generic to a lot of cases. I mean, the big one that I tend to think about for this is the transition to turbulence in very, very fast-moving fluids. So there's a famous experiment from the 1970s and 80s, which was one of the first to show this. Sorry that the contrast is not great there, because it has a transparent background. And the basic idea here is that I have something like a tank of water. And inside that tank of water, I have a bunch of fluid that's in this annular region between an inner cylinder and an outer cylinder. And this experiment from the 70s is super simple, which is that they're going to increase the speed of rotation of that inner cylinder. And it's going to go from just having normal flow between the cylinders, it just sort of moves in this nice azimuthal direction, to eventually, once you get fast enough, you break down in symmetry and it looks like, and you get turbulent flow in that cylindrical tank experiment. So this is the diagram of the setup, but what that actually looks like here is that if you watch that cylinder from the side and you put in a fluid that sort of shows you the shear, so you put in particles to track it, at low speeds, you get sort of convective rolls that align with the streamwise direction. Then as you go a little bit faster, you get this higher order term here that corresponds to sort of oscillations off that symmetry. And then when you get faster and faster, those sort of like excitations start to overlap with each other. And eventually they overlap enough that they sort of break down and you get rise to fully developed turbulence. And this idea that I start out by having a dominant harmonic here, but then I sort of see that I have some higher order term, then maybe I have some more terms, and then eventually get chaos. This is extremely similar to the period doubling route to chaos, where I went from having one dominant resonance to having two, to having four, to now having a bunch that are interacting, giving rise to fully developed turbulence. And we'll talk about what that means a little bit more sort of mathematically towards the end. But this is the basic picture here, is that this period doubling route to turbulence actually happens in real fluid experiments. And I think that, and this is, I think, this is an old picture, but this is, I think, a slightly nicer picture I found that sort of shows you a little bit more clearly what's going on, where that harmonic appears and then eventually you get full turbulence. So period doubling is pretty generic, and it happens in continuous time systems that you can observe in a laboratory. Okay, so rather than thinking about period doubling as, I went from having 2 periods to 4 periods to 8 to having, in principle, many different timescales in my problem, we're going to think about what that looks like in the Fourier domain, where I go from having 1 excitation to 2 to 4 to having many. Yeah, what's up?
Just a physics question. So is it always true that the period only doubles and not like triples or like from 1 to like 5 or something?
Yeah, so that's what's cool, is that so part of the reason that you have these discrete modes is because you have boundary conditions in the tank. So that does provide like a discretization scale. But modulo the fact that you have boundary conditions, the actual mechanism where you go 2, 4, 8 is actually generic to a huge class of systems. And this is a cool result because it was found in the 70s and 80s, despite being a very fundamental mathematical property. That's part of why people like me think chaos is so cool. Okay. So I want to study time series that capture an aspect of this experiment. And I wanted to actually do a full simulation of this for today, but I decided that was computationally too heavy. So we're going to study this phenomenon in a really reduced model of this experiment. And it's going to be kind of incredibly reduced, but still is going to capture the fundamental period doubling. So this is going to be a dynamical system called the Rossler system. We're not going to get into the structure of the actual how we integrate this or anything. We're just going to assume that it's given to us. but this is going to be a 3-variable dynamical system that exhibits very similar properties of the actual full period doubling cascade to chaos. So the idea here is I have 3 dynamical variables, and if you want to think about these in terms of the Taylor coadder, in terms of the turbulent flow experiment, you can think of our dynamical variables as something like if I have a velocity field as a function of r. Wow, that's terrible chalk. If I have a velocity field, I was all the way over there. If I have velocity field as a function of r, right? So in principle, this is an infinite dimensional dynamical system because this is defined at every lattice point. We're going to assume that this reduced order model is something like the space averaged velocity field, or something like that. So we average out over r, so we get a single number. And this is actually pretty realistic because a lot of old-timey experiments didn't have very good imaging. So they basically just got an average velocity in their tank or something. So dynamical variables might be something like this, and they might also be the time derivative of this. Where I use, in my notation, I tend to show the variable we integrate over as the subscript here. That's just how I tend to do these averages. Okay, so this is going to be a 3-dimensional dynamical system, but you can think of those dynamical variables as something like order parameters or something like the mean velocity in the tank or the mean change in velocity or something. It's a bit idealized, but it captures the key sort of properties of this experiment. Okay, so this is a 3-variable dynamical system. I'm going to implement it as a class or whatever, but we don't really need to worry about that for now. I'm just going to integrate it. But basically, I'm going to try to solve for the average velocity, the average change in velocity, and these other variables as a function of time, 4 different values of the speed at which I'm rotating the tank. Okay, so what that does, and I'm going to go ahead and run this, and hopefully I have that in my memory. All right, good. Okay, so when I do that, I get in the if I at a certain value of parameters, I get something that looks a lot like the logistic map, which is that this is a continuous time system, but it still exhibits chaos. So my variables that describe my experiment over time fluctuate erratically. So this is chaos in a continuous time system as opposed to discrete time like the logistic map, but it has the same property where if you look at it over time, none of my variables I'm tracking repeat themselves. I have 3 of them instead of 1, but it's the same basic idea is that it's a non-periodic trajectory over time. Okay, so this is just a kind of toy model. It's a low-dimensional set of ODEs, but you can think of it as capturing some properties of the full infinite-dimensional turbulence experiment. Importantly, it exhibits chaos with this very sort of complicated set of things it does over time. Okay, so these are my 3 variables over time, but because I have more than one dynamical variables, it's usually helpful to plot them against one another. So here I'm going to take 2 of my variables. There are 3 total, but I only can draw 2 in 2 dimensions, and I'm just going to plot them. And it turns out that the attractor of this system looks like this. So if I have something like a turbulent flow, the attractor is infinite dimensional, but the nice thing about working in reduced order coordinates is I just have a 3-variable dynamical system. So the flow over time, if I think of it as occupying some state space, it creates this really complicated sort of folded object, where this is just these coordinates plotted against each other parametrically. Okay, so this is my sort of idealized model of a turbulence experiment, where I have these low-order variables that exhibit chaos over time, that I argue are very similar to what the mean velocity in that tank would do if you were observing it over time. Okay, so the reason I chose this dynamical system as our sort of toy model of this turbulence flow experiment is because this continuous time system actually exhibits period doubling, the exact same mechanism of period doubling that you'd see in the full experiment. So what I'm going to do here is I'm going to reintegrate that dynamical system, but I'm going to change a parameter of the system that's analogous to the speed of the inner cylinder. So you'll recall that you get this formation of turbulence when I increase the speed of the inner cylinder. That's a parameter of the underlying simulation. So I'm going to change that parameter to simulate speeding up that inner cylinder and seeing whether turbulence appears. So that's this model C that defines my differential equation. And I'm just going to simulate what the system does as I increase the value of that effective inner cylinder speed, which should give rise to turbulence. Okay, so I'm going to go ahead and run that. I think it ran. Okay, cool. Okay, so here I'm just going to plot one of my coordinates over time to help it be a little bit clearer what we're seeing. So this is when I have the low flow speed, and you can see I just get oscillations. This is when I have a slightly higher flow speed. And I'd argue that this corresponds to a period doubling. The idea is that I still have these peaks, but now I have this clear sort of second harmonic where it goes up and back up, then down. So I got a period 2 because I have 2 characteristic timescales there. Then the next one, I increased the flow rate just a little bit more. And this is, I think, legitimately hard to see. But I'm going to claim that if this is period 2 and this is period 4, that this is period 8. And the reason I'm going to say that is because if you look carefully, it goes up, it comes down, goes up. This peak isn't as low as that peak there. It's a little bit hard to see if you don't like kind of magic eye it. But really the recurrence isn't here, it's here. It's a little bit hard to see, but I'll plot it again in a way that'll make that more obvious. So my claim is that this time series has double the period of this time series. It's clear that this and this is doubled, but I'm going to claim that this doubles again. And then I increase that parameter that corresponds to the speed of the cylinder even more. And now you can see that it's non-repeating. I get these crazy sort of intermittencies where it never repeats itself. And interestingly enough, you'll see that even in the chaotic system, you see what look like sort of flashes of the previous solutions, but they're stitched together in a way that never repeats. So you can sort of see this like simplified model of how turbulence forms in this really low order reduced set of ODs that describe this experiment. Okay, so that's a little bit hard to see if I just plot the trajectories, but I think it's a lot easier to see if I just plot the coordinates themselves. So if I plot my 2 dynamical variables versus each other, you can see you get a limit cycle at the low speeds. Once I increase that parameter, you get a period 2 limit cycle. Increase it again, you get period 4. And then the chaos thing looks like a bunch of different limit cycles on top of each other. So that's what the period doubling route to chaos looks like in continuous time. Okay, so the reason I like this is because we can start to see what maybe the spectrum of the system is going to look like, right? Because we went from having 1 limit cycle to 2 to 4 to what looks like a whole bunch of limit cycles stacked on top of each other. So that tells us that maybe the number of excitation modes of the system has increased in some abstract way. Okay, so that's the basics of period doubling in continuous time, but it's all the same as what we saw in the logistic map. It's just that we have to do more dynamical variables because it's a continuous time system. Okay. So I have these nice time series I've created, right, which show me in principle, right, that, oh, that looks like that's twice that, but it would be nice to actually quantify that. So to do that, we're going to perform some Fourier transforms on this data sets. And rather than just using built-ins, we're going to do it the hard way, and we're going to try to re-implement Fourier transforms from scratch, just so we can get some intuition behind what they do for this problem. Okay. So, I think we've all seen Fourier transforms before, but the basic idea is that I have my time series. You can think of this as like my mean velocity in my Taylor-Couette experiment, or whatever your time-dependent variable of interest is. And I want to decompose that signal into a series of trig functions, which are periodic, amplitude, which each have their own amplitude and frequency. So I like to think of the Fourier transform as taking a signal and breaking it into a histogram, where that histogram basically tells you how much of each frequency is present in the signal. And for our purposes, we don't care that much about the phase today. We really just care about what these coefficients are of these different harmonics that make up a signal. Okay. So for my time series, you can, for my Taylor-Couette or for my turbulence experiment, right, I'm going to basically have some time-dependent signal as a function of time, right? This is my turbulent case, so it does a bunch of crazy stuff over time. And I want to break it up to see how much it looks like this sign versus that sign versus that sign, et cetera, et cetera. So I want to decompose and say how much of each of these modes is present in my system over time. And that should tell me what this amplitude A is, which tells me the degree to which this particular harmonic contributes to this frequency. And you can already guess from the way I've set this up that in a chaotic system where I have things like period doubling, that spectrum is going to be really informative because it tells us something about how many harmonics are present in the signal. Okay, so I want to map this signal, which you can think of as a vector in t dimensions, where t is the number of time points, into how much it's similar to this signal versus all the way down to some super high frequency oscillation. Okay, so naively, this is a relatively simple thing to do numerically. So if I think of my time series in one dimension as just a vector with t elements, or here, I guess I'm using n here, where n is the total number of time points. In principle, I can basically just find these Fourier mode amplitudes by projecting this vector onto every single one of these harmonic vectors. So the naive way that you could imagine taking a Fourier transform of this system is basically by performing a series of dot products between my time series, which is a one-dimensional vector of length n, and a whole bunch of additional vectors of length n, which each capture each one of these harmonics. So rather than do those dot products by hand, you could write that as a matrix equation. So I'm going to build a giant matrix M that basically every row is one of these harmonics. And I'm just going to take that big matrix and take the inner product of that with my time series. And that's going to give me estimates for the coefficients of my Fourier transform. So worst case scenario, right? I can think of a Fourier transform as projecting my system onto a new basis. That requires a series of dot products. I'm going to arrange those as an n by n matrix times my length n vector. And that will give me a length n vector that corresponds to the coefficients of this transformation. Okay. So the first thing I want to do is, so the nice thing about that is that once I know n, I can build this matrix in advance because m doesn't actually care about x. M is always the same. It's just how much of each of these harmonics is present. So the first thing I want to do is build that matrix. So I'm going to show what that matrix looks like because I think it looks really cool. Okay, so I'm going to build this matrix M that we're going to dot with our signal. And that matrix actually looks like this. So that's not the screen, that's actually like what it looks like. But basically, if I take a line scan across this top thing, I get one big hump, right? That's the lowest order sine function. And then each of these additional terms, I'm just increasing the frequency by 1 over n. And so then here you have this really rapid oscillation that corresponds to the highest frequency present in my image. So each row of this is one of these pictures all the way to 512 is what I used here. And I can make this a little bit easier to see if I go to, like, let's say I do 64 or something. So you can kind of see this crazy structure there where at the middle, it has the highest frequency that you can get. And importantly, once I specify n, the size of this matrix and all of its elements have been fully specified, right? This is always the same, doesn't care about the signal. So M is just some big matrix I can pre-compute if I need to. Okay. So I'm going to go back to 512 because I think my axes bounds prefer it. Okay, and just to give an idea, so these are a couple of rows of that matrix. So that's the top row, that's the middle row, and this is the dead center row. It has this really crazy stuff, right? And these are what I want to dot product with my signal by taking this giant matrix transform. Okay, so this is kind of a naive view of a Fourier transform, right? It's just a big dot product with a bunch of basis functions that all have the same size. So we're going to implement that. We're going to implement this one operation of this known matrix times the signal. We're going to implement that in Python just as a linear transformation of the signal. So I did this a little bit fancy, just I don't know, just to show off classes, but I'm going to define a base class that's a signal transform class. So this class is going to take my signal, it's going to center it and do a couple of sort of nice things to it to make it a little bit easier to work with. But then it's also going to compute the frequency bounds of the signal. So this basically corresponds to what the highest and lowest resolvable frequency are. And those of you who are familiar with the Fourier transform lore probably know that in discrete time, there's a maximum number of observable harmonics, and that's what this calculates here. So I'm going to build this base class for transforming a signal that does these nice things, and then I'm going to inherit it in a discrete Fourier transform class. And this discrete Fourier transform class is going to implement the logic where it takes the signal, runs this pre-processing, here it's just zero centering it. Then it's going to, based off the length of that signal, find out how many frequencies we can resolve. It's going to build this giant M matrix. So this line right here is equivalent to finding this giant matrix for that signal length. And then it's just going to do a dot product between the matrix and the signal. Okay, so that's my implementation of a discrete Fourier transform using just sort of vanilla methods. It's just a giant matrix multiplication. So let's see if that works. I'm going to go ahead and calculate that for... Okay, so here I'm going to go ahead and calculate that for a bunch of time series that I just computed. So this loop is going to loop over my period 2 time series, my period 4, my period 8, and my chaotic time series from my turbulence experiment. Okay, so when I do that, I get kind of what I expect, which is that my Fourier transform for the period 2 case, it has these harmonics, which if you read off the axes correspond to the frequency that you observe when you just look at that oscillating signal. Everything go to my period 4 case, I get twice as many harmonics, so that tracks with what we'd expect. I give it my period 8 case. We're starting to run out of resolution, but you can see I'm starting to get additional humps that correspond to that period 8 case. And then I give it the chaotic case, and it's just all over the place. And this is going to give us some intuition that we're going from having a couple of modes that are excited, right? 1 limit cycle, 2 or 4, however many, to having a whole bunch of structure at a bunch of different scales. So chaos is sort of the formation of this case where you have many different limit cycles instead of just a discrete countable number. Okay, so that's what the Fourier transform looks like of a system as it goes from showing limit cycles to faster limit cycles to eventually showing chaos. But the nice thing is that you can observe this purely experimentally just by doing this giant dot product. Okay, so that's the vanilla Fourier transform. But the question is whether I can do this any faster. Because if you think about this calculation I just did, all I had to do was define this giant matrix. The size of that matrix is n by n, and I have to multiply that by my signal, which is length n. So if you think about what a dot product entails, right? A dot product involves taking every element of a vector, multiplying it by another vector, then summing them all up at the end. So a dot product between two vectors of length n should have a runtime that scales as roughly n. However, my matrix is just a stack of n of those vectors, and so I expect my full matrix vector multiplication to be n squared. Another way to think about that is I use every element of that matrix once to do a dot product with the vector. So my discrete Fourier transform implemented the way I've done it should take roughly n squared operations because I'm doing n dot products with n length vectors is how you can think of a matrix vector. Okay, so my naive Fourier implementation is n squared, which is not that bad, but there might be ways to do better is kind of going to be the point that we'll get to. Okay, so that's the discrete Fourier transform. It's just a bunch of matrix multiplications. Okay, yeah, what's that? Yeah.
So in the graphs that you just showed,
Yeah.
so the maximum peak would probably be at like, let's say if you were considering the period doubling case, it would be at 2, like the frequency.
Yeah, so I really, I guess the frequency is 1 over this time scale here, which has some weird gobbledygook units, right? But whatever that time scale is what I should get as my biggest peak, yeah. And then I'm just getting harmonics because I'm repeating the pattern, yeah. Okay, so the question is, can I do any better than n squared on this problem just by thinking carefully about the structure of this? And the intuition for why you might be able to do better is if you look at this big matrix, there's obviously structure here, right? So if this matrix just had random elements, right, then I would probably not be able to do better than n squared. But the fact that there's a lot of repeated structure in this matrix is a clue that there might be an acceleration available that will speed up the runtime of my algorithm. Okay, so this is a little bit, I don't know, this is a little bit of kind of a derivation. So I don't know how much I want to get into the nitty-gritty on this because I want to get to the actual code. But the idea is kind of simple, which is that if I have some Fourier transform and I perform a shift on that transform by an integer multiple of n, I will get the same, I'll get the same Fourier coefficients back out. So in other words, Fourier transforms admit circular shifts on the space of integers. I don't have a nice picture for going through this, but if you just plug in an integer multiple of n into this calculation of the Fourier transform, which is the definition, you sort of factor things out and you remove terms that are equal to 1. You can prove that this is the case, that any multiple of n gives you back the exact same Fourier transform sequence. Okay, the reason that that's useful is because right now when I write my matrix multiplication, I have to do this whole sum of all these elements from all the way from 1 to n, from 0 to n minus 1, so that's n total summations. But because of this property, I can actually simplify that by splitting this calculation into the sum of 2 terms that just require half of n. So in other words, I can reduce my computational requirement from having to do all n of these multiplications to just doing n over 2 plus this additional operation here where I combine these two. And that's due to this symmetry where there's this shift there's this shift on the space of allowed sort of basis functions, which captures this idea that these are sort of self-similar to each other when I go down this matrix. So this derivation, I don't know, it's just basically sort of moving symbols around. But the important thing is that I can write the Fourier transform, which is the sum over n, in terms of 2 terms that are sums over 1 to n over 2. So this is kind of nice because it suggests that instead of having to compute a full length n dot product, I can instead compute 2 length n over 2 dot products for this. And if you want to write that down as pseudocode, if I have my time series, which is a bunch of elements from 0 to n, I could split that into an even and odd time series. take the Fourier transform of those two half-time series, and then just combine them to get my total Fourier transform. So, and you can think of it as like, this is like split, it's like sort of the inverse of merging a deck of cards where I take every other card and I pull it into two decks, where I've basically taken every other element and decimated the time series to get these two things. And importantly, I haven't discarded information, right? Every time point remains the same. I've just sorted them into these even and odd sets, which I'm then going to separately Fourier transform, then combine at the end. So that's a lot of sort of moving symbols around, but you can actually implement it using my discrete Fourier transform to prove to yourself that it's the case. So what I'm going to do here is I have my DFT, I compute it, I get some spectrum. Then I'm going to do the exact same thing where I split it using NumPy slicing notation. I'm going to take every other element, then I'm going to take every other element starting at 1, so that's the odd elements. I'm going to separately compute the Fourier transform, and then I'm going to add them together. And you can prove to yourself with some moving symbols around that these steps implement this logic here. Okay, so I've split my Fourier transform, which takes n products into two n/2 operations. Okay, so let's go ahead and run that and confirm that it does give me the same answer. Okay, so that's my normal Fourier transform using the full dot product. These are my two half transforms. They look pretty similar to me. Yeah, you can even see the same like distance structures there. Okay, so that's again due to the shift property of Fourier transforms, but that's nice because you can already tell I saved a little bit of compute by doing two half transforms and merging them together. Okay, so the idea of the fast Fourier transform is to basically do this splitting on steroids, right? Because I just said, oh, I have a Fourier transform, I can split it into two halves by taking every other element, and now I can save compute by doing two half transforms. But I could go crazy and I could take each of those half transforms, decimate them again, and then perform 4 quarter transforms. Or I could split it again and perform 8 transforms, right? So I can basically take that logic that I can split a Fourier transform into smaller transforms on every other symbol, and I can keep applying it to my time series. And this is where we're going to see a very, very clever use of recursion by Cooley and Tukey, who invented this algorithm back in the 60s, I think. Because the idea is that if I have a signal, rather than ever touching a true Fourier transform, I'm basically going to keep splitting it into half signals until I get down to the trivial Fourier transform, which is when I'm given a single symbol. So I'm going to divide this time series of n elements into first 2 half time series, then 4, and I'm going to keep decimating it until I just have a bunch of individual terms. And the reason that that's useful is because it's actually super easy to find the Fourier transform of a single symbol. The reason that's going to be useful is because this structure where I perform my half transforms all the way down until I get single symbols, then this gives me a recipe for building the transform back up, right? Because we saw here that once I have these half transforms, I can compute the full transform by sort of interspersing the elements of the half transforms. So once I've done this all the way down to single symbol transforms, I can then build the 2 element transform by combining with this rule. From those, I can build the 4 symbol, then the 8, all the way back up. So I'm going to go all the way down by splitting up this vector, by splitting off every element, take the transform, and just merge them back together using the inverse of this rule. In the structure where you go down all the way until you hit a base case, that's when you're doing a Fourier transform of a single element vector. Then I hit that base case and I go all the way back up, gluing everything back together. This is exactly the core of what recursive algorithms do, right? Which is that you keep applying the same operation. Here, that's this riffling where you take every other element until you hit a base case where you just have a single element. That's your trigger to revert that cascade. You start gluing stuff together and eventually get out your total Fourier transform. So the math on that, I don't think is super transparent, but I think the code is a little bit easier to see. So my fast Fourier transform implementation, just like my DFT, it has a transform method, but now I'm going to write something different here, and I'm still going to inherit from my same signal class. So this is going to have a recursive structure where I'm going to pass my DFT my signal. It's going to get the length. If that length is 1, that's my base case. It's going to trigger a return. But if my length is not 1, it's going to split the signal into every other element, then pass both of those separately to itself. So just like every other recursive function, it's going to call itself on a decimated version of the series. And you'll notice that I'm giving it the even numbers here and the odd numbers here. And so if I have something like, I don't know, an 8 element time series or something, this is going to call itself 3 times, right? Because 2 cubed is 8. And so it's going to see that it had 8 elements. When it sees that, it's going to call itself, then has 4, it's going to call itself, 2 calls itself, then finally it hits this. This return passes to the deepest one of those that will stick them together. That then returns higher to the next highest one up, and you sort of will invert that entire cascade of going deep. And so if this is a little bit weird, I don't blame you, but one way to think about this is that I could replace all of this logic by explicitly taking all of these steps and just writing another sort of nested if condition where if n equals 2, I do something else, and I could go deeper and deeper until I had a full 8. The nice thing about doing it this way is it's agnostic to what n is. Okay, so this idea of splitting this array into parts and going deeper and deeper in recursion in order to avoid having to sort of ever take a Fourier transform of a full length n array, this is actually going to give us pretty significant speedups compared to vanilla Fourier transform. Right, so we know that a normal Fourier transform involves a giant matrix vector multiplication, which always has n squared, where n is the length of that vector. This sort of fancy Fourier thing where you split the thing into halves and you only perform on half of the array at each time, it's structurally very similar to binary search, what we saw before, as well as merge sort, which is in the textbook. In that second transformation where we iterate over all the elements of the array, so we perform this series of dot products, we can replace that factor of n with a log n factor. And so as a result, the complexity of the fast Fourier transform, which has this recursive structure, that ends up being equal to n log n, where we have n because the length of our time series is n, so we have an inevitable number of operations we have to perform. But the log n comes from the fact that we don't have to look at every single row of this giant matrix. Instead, we can look at half of the matrix at each point. So is this kind of like, some people talk about fast Fourier transforms as like performing a binary search in frequency space, because the actual complexity is equivalent to avoiding looking at every element of that giant M matrix and instead looking up half the elements at each time. So this seems like a really minor difference, but this going from n squared to n log n actually has pretty big asymptotic implications. So here what I've done is I've done a timing test where for something like 2 to the 9 elements, I get a factor of about 2 speed up, so modest but still noticeable. But if I then increase the size of my signal really, really quickly, you can start to see that you get a real advantage from doing the fast Fourier transform. So as the size of the signal increases, the fact that you have an n log n scaling versus n squared really starts to pay off. And this is generally useful, right? Because most time series that we encounter in the real world are things like clickstream data or time series from experiment, where you could have billions or trillions of elements or streaming data. So not having to compute this giant n squared matrix and instead being able to do this nice n log n speed up, this can actually get pretty significant. And that's part of why the fast Fourier transform is talked about in the book as one of these really important algorithms in history, because this one really kind of clever idea that these authors had gets you a speed up that I can even see on my own, local machine, which I think is really cool. And it's all just using the fact that you can think of Fourier transform as recursive, but the intuition for why this is possible is that the actual matrix operation I'm doing has some real redundancy that's noticeable in the structure of that matrix. So you're sort of leveraging redundancy to avoid having to compute element-wise products of every member of this matrix. Okay, so that's the fast Fourier transform. Your book has a very different framing of this. So this is this press textbook. They talk about it a little bit more as a search algorithm, which I think is kind of an interesting framing. But generally, this idea that you have recursive structure is a very cool, non-trivial algorithm. Okay. So the last thing I wanted to talk about is maybe to return to this question of why do we care about taking Fourier transforms and what does that tell us about physical systems? So we saw this example above, right, of what happens when I take the Fourier transform of my turbulent flow, right? Where if my turbulent flow is doing this kind of crazy thing, if I have a case where it's not quite turbulent yet, right, I expect to see this case has a spectrum that looked like this, right? Then the case where it period doubled had a spectrum that was a little bit more elaborate. Then it got a little bit crazier, and then eventually it got really, really elaborate. So that basic insight that period doubling route to chaos gives rise to doubling in your Fourier spectrum, this is actually the basis of a really famous paper by an emeritus member of our department. So this is an experiment where they quite literally built the rotating tank experiment. They actually used to have it up on the 14th floor here. where they basically built that giant thing of liquid. They spun it really, really quickly in order to control whether turbulence would break out. And then they didn't have the ability and the time to get these really high resolution recordings, so you can't see the full flow field. So instead, they just measured the average optical path length as you view the tank. So they basically got a single number readout from their experiment, which is something like a time series equivalent to the average velocity inside the tank. And so that's kind of cool because they get a one-dimensional signal that basically summarizes their entire experiment. And when they did that experiment, this is a PRL paper from 1975. At low speeds, they get this nice periodic thing, and they see these well-placed peaks. Then they sped it up a little bit. They saw harmonics break out. It got a little bit crazier. And then when it finally approached turbulence, they got the first hint of a continuous spectrum. And so this idea that you sort of period doubling manifests in the physical structure of the harmonics was actually the basis of this really, really famous discovery of how turbulence forms in fluids. And this is a celebrated result in nonlinear dynamics because it connects things like the logistic map, which is a toy, to really hard experimental observations that they were able to see in the rotating tank. Okay, so that's what I wanted to say about the Fourier transform. And I'd say that, if you haven't seen recursion before, I think the book is a very different way of doing it. So I'd encourage you to take a look at that. Thank you.